So next lesson on the capacitors will be uh, separation of voltage among capacitors. Separation of voltage among capacitors. So we're going to learn this capacitors. Imagine there are two or more capacitors in a circuit. Now we are connected to a battery. We are going to study how is this voltage of the battery separated among the capacitors. Now, if you consider a circuit with resistors from your O levels, that is not that hard. Now, let's say there are two resistors like this. This we will be learning in A level as well. The next unit. Imagine this is 10 volt. This is 2 ohm. This is 3 ohm. Okay. Now, when now current is going to flow through the system. When since they are in series, same current will flow through both the resistors. Now my question is, what is the voltage across each of these resistors? What is the voltage across each of these resistors? So I'll take 2 ohm as R1, 3 ohm as R2. First, let me explain with resistors with what you know from O level. So I'm going to find out what is the voltage across this, what is the voltage across this. Now we know for this we can use the equation V equals IR, Ohm's law. Therefore V is equal to IR. Now V1 it's going to be equal to IR1. V1, I'm applying the equation for this resistor. Huh? So voltage across this is V1, current is I, and the resistance of that is R. And if you apply it for the second resistor, that is going to be V2, different voltage, equal to same current, I, R2. Okay, right. So when you consider these two equations, if you divide them, you will be getting V1 over V2, V1 over V2 is equal to R1 over R2. That means this voltage divided by this voltage will be, that ratio between the voltages will be equal to the ratio of the resistance. Right. If R1 is 2 and R2 is 3, it's 2 by 3. Okay, ultimately we have V1 over V2 equals 2 by 3. So this total voltage 10 volt is going to be separated in the ratio 2:3. So finally, what is the answer? V1 is going to be, how do you separate 10 in the ratio 2:3? This will be 4 volt. V2 will be 6 volt. 4 and 6. 4 and 6. These are some ordinary level maths and ordinary level physics. But it is for resistors, not for capacitors. Now we'll do the same thing for capacitors, and let's see how it works with capacitors. All right, that's what we're going to do. Now let's consider a circuit like this. Okay, let's consider a circuit like this. I'll take the voltage of this battery as V for the time being, and there is a capacitor here, capacitance of C1, here capacitance of C2. Okay, so the potential drop across this is V1, the potential drop across this is V2. And in the previous class, we learned when you have two capacitors in series, same current will flow through those capacitors for same time. Same current will flow through those capacitors for same time. So once the system reaches steady state, what do I mean by steady state? Once both the capacitors have got charged, both the capacitors will have equal charge stored in them when they are connected in series, always. When there are two resistors, through those resistors, equal current will flow. When there are two capacitors in series, across them, equal charge will be stored. Right? Fine. Now let's consider this. We know the equation is Q equals CV. If I apply this equation for the first capacitor, C1, equation is going to be Q equals C1 V1. C1 is its capacitance. V1 is the voltage across them. And if I apply the equation for C2, it is going to be Q equals C2 V2. Q equals C2 V2. That is the second equation. Right. Now, when you take the first and second, you should be able to understand they are the same equation. Therefore, 1 is equal to 2. You can say C1 V1 equals C2 V2. Therefore, V1 over V2, it's going to be C2 over C1. Not, it's not as same as resistors. You gotta be really careful here. Now, for the benefit of your comparison, I will quickly consider the circuit with resistors as well. I just explained this little while ago with the derivation with current. Voltage, if you take the voltage as V, resistance R1, resistance R2, and the voltage across this is V1, V2. What was the ratio between V1 and V2? V1 over V2 was equal to R1 over R2. But in capacitors, it is C2 over C1. Okay, higher the capacitance, lower will be the charge. Lower the capacitance, higher will be the charge. But here, higher the resistance, higher will be the voltage. Lower the resistance, lower will be the voltage. That's how it works. All right. So we have to be really careful here. Now let me quickly explain you with an example. Let's imagine a system, a circuit like this, where there is a battery and there are two capacitors. Right. Um, if you come across a situation like this, now let's say this is 7.5 volts, whereas this is 3 microfarad and this is 2 microfarad. Yeah, I'll say take that C1 and let's say this is C2. Now you are supposed to find out V1 and V2. Now what should we do here? So let's go with this equation. So we know V1 over V2 should be equal to C2 over C1. Okay, so what is C2 over C1? C2 is in fact 2 and C1 is 3. So V1 over V2 is 2 is to 3. V1 over V2 is 2 is to 3. Now 7.5 volt is to be separated in the ratio 2 is to 3. I mean V1 is to V2 is equal to 2 is to 3. Okay, so total, if total as a total there are 5 parts. Out of those 5 parts, 2 for V1, 3 for V2. So if you want to find V1 with an equation, then you will write like this. Out of 5, 2 for V1 multiplied by what is the total voltage? 7.5. So that will be, if you simplify that, it's 3 volts. And V2 out of 5, 3 for that into 7.5. And that is 4.5 volts. So 3 volt and 4.5 volts. That is how it works. Okay. Right. Now, when there are two capacitors, it's not that hard. You can conveniently use this equation and get the answer. But things get a little complicated when there are 3 or more capacitors. They will not go beyond 3 as far as I'm concerned, most probably. They won't go beyond that, right? Now, let me quickly explain you what's going to happen when there are 3 capacitors. How are we going to use this concept, right? Fine. So let me quickly consider a circuit where 3 capacitors are put in series, and then there is a battery like this. Okay, this is V, the total voltage. I mean the voltage of the battery, and the capacitance. Let's take it as C1, C2, C3. So our concern is what are the voltages across each of these capacitors? V1, V2, V3. Let's say the charge now. Charge is going to be same Q, Q, Q. Same charge is going to be stored. All right. So we can consider an equation like this: C1 V1 equal to C2 V2 equal to C3 V3. I mean, if it's confusing to you, we all know Q is equal to CV. Q is equal to CV. So all three capacitors, same charge is stored. So C1 V1 equals C2 V2 equals C3 V3. Right. Now, now, since you have 3 parts now, what we can do here is you should be writing that in this way. I mean, how do I put that? You can write it this way, people. V1 to V2 to V3, you can write it as 1 over C1 to 1 over C2 to 1 over C2. You can consider it this way. Okay, I mean, we got V1 over V2 equals C2 over C1. I can write it like this also now. Yeah. V1 is to V2, or else, yeah, wait a minute. Okay, wait. V1 over V2, you can write it like this. C2 over C1 can also be written as 1 over C1 over 1 over C2. Hope you can agree with me on that. You can write this 1 over C1 over 1 over C2. So from that, I can say V1 to V2 equals 1 over C1 to 1 over C2 for two capacitors. But when you consider like this, it's a bit complicated. That's why I did not teach you this method for two capacitors. All right. For two capacitors, this is the easy method. But when there are three, you can't write V1 or V2 or V3. No, there's no such thing like that. So you have to go for the ratio system. So this is how the ratio comes. All right. Now this is note for three or more capacitors. For three or more capacitors, this is how we are going to use. At the same time, if you come across resistors, what will you do for three or more resistors? For three or more resistors, it's going to be the other way around. It's very easy, straightforward. Let me quickly draw this diagram for you. Right, so one resistor, two resistor, three resistor. It is R1, R2, and R3 is V, and across each the voltage V1, V2, V3. They are the voltages. Give me a second. Now this is R1, this is R2, this is R3, and if you take the voltages as this is R3, R3. This is voltages. If you take them as V1, V2, V3. This time it's easy. So here it will be V1 is to V2 to V3 will be directly R1 is to R2 is to R3 because it's proportional, but here reciprocal. Okay, so this is also important because there are questions, past paper questions where there are three capacitors taken into consideration. Okay, so remembering just this is not good enough. You should be able to apply that to questions and see if you can get the correct answers. That's also crucial, right? Fine. This is one and this is the other. Now let's choose an example and let's see if we can apply that correctly. Right, so let's deal with numbers. Example, find the voltage across each capacitor. Right. Think of a situation like this. Okay, now this is a system and the voltage of the battery is 6.2 volt. All right. So your task is finding the voltage across each of these capacitors, V1, V2, V3. Okay, right. Now let's find this out. When we have three or more capacitors like this, what we have to do is we need to use this ratio V1 to V2 to V3, and that will be given by 1 over, okay, that is actually 1 over C1 to 1 over C2 to 1 over C3. That is actually 1 over 2 to 1 over 3 to 1 over 5. Now the um, problem is these are not integers. So you have to convert them to integers. And hope you have learned that in your ordinary level classes. What do you do to convert them to integers? You have to multiply each of these fraction by the least common multiple. For 2 and 3 and 5, what is the least common multiple? I think it's 30, isn't it? It's 30. The least common multiple is 30. So you multiply everything by 30. When you multiply everything by 30, half into 30 is 15. 1 over 3 into 30 is 10. 1 over 5 into 30 is 6. That is the ratio, right? So how many, what is the total portion, number of portions here? 15 and 10 and 6, that is actually 31. We have 31 parts. Out of those 31 parts, 15 for V1. Out of those 31 parts, 10 for V2. Out of those 31 parts, 6 for V3. Therefore, if you want to find voltages, V1 in equation form, V1 is going to be equal to out of 31, 15 into the voltage 6.2. That's why I put 6.2 there, so that 31 and 6.2 can be simplified conveniently. When you simplify 31 and 6.2, here it will be 0.2. 0.2 into 15 is 3 volts. V2 will be equal to 10 over 31 into 6.2. So that is 0.2 into 10, that is 2 volt. And then automatically what is V3? You can find it by subtracting these two from this. Okay, that is one method, that is 6.2 minus 2 minus 3. And that will give you 1.2 volt. If not, you can also find out V3 this way, 31 over 6 into 6.2. 0.2 into 6, that is again 1.2 volts. So these are the voltages, 3, 2 and 1.2 using this equation. And how did I get this? By multiplying by LCM. All right. Now let's approach a different question. Same concept, but a different approach. Let's say they have given you a system like this, where a battery is connected to 3 capacitors, and the capacitances are 2, 3, 1 microfarads respectively, and the potential drop across 3 microfarad capacitor is 0.4 volt. If so, what is the voltage of the battery? That is the question. Okay, right. Right, fine. So here, let's take this as C1, C2, and C3, something like that. So this is actually V2. This is V1, and this is V3, something like that. Okay. Now, what is the relationship between the capacitors and the capacitance and the voltage? That is V1 to V2 to V3 is given by 1 over C1 to 1 over C2 to 1 over C3. Right. Then V1 to V2 to V3, that will be 1 over C1 is 1 over 2, 1 over C2 is 1 over 3, 1 over C3 is 1 over 1. Like I said before, you can't work with this. You have to change that to ratio in integers. You have to multiply them by the least common multiple. 2, 3, 1, the least common multiple is 6. 2, 3, 1. You multiply by 6, half into 6 is 3, 103 into 6 is 2, and 101 into 6 is 6. So we have 3, 2, 6, and altogether we have 11 portions. 11 portions. All right. Out of those 11, we are going to give 2 to 3 microfarad. So if you write the equation for V2 like we did before, V2 is going to be equal to 2 over 11 into total voltage V. V2 is equal to 2 over 11 into V. Total voltage is what we are supposed to find out, and V2 this time is given to us. That is 0.4 equal to 2 over 11 into V. And 4.4 divided by 2 is equal to V. So V will be equal to 2.2 volt. That is the final answer. Okay. A reverse approach. Over question. Now the next circuit we are going to consider is this. There is a battery and there are two parallel paths. And in one parallel path, there are 3 capacitors connected in series. In the other one, there are only 2 capacitors connected in series. All you need to do is you have to find the voltage across, find the voltages across 4 microfarad and 5 microfarad. Okay, go ahead. Right, now, whenever they give you a parallel system like this, first and foremost, you have to understand, in fact, you have to understand is this path and this path, both will have the total voltage across those paths will be equal to the voltage of the battery, because they are connected in parallel. So when something is connected in parallel, the idea behind this is the total voltage across that system is equal to the voltage of the battery. So here the total voltage is going to be 2.8. 2.8 will be across this system as well as this system, 2.8 volts. Okay, right. And then that 2.8 must be separated to each. I'll quickly do it now. It will take it as V1. Here we'll take it as V2. Here we'll take it as V3. Now we need to find out V2. We need to find out V2 out of these three. And here I'll take this as V4 and V5 very quickly. And we need to find out V5, right? Let me give me a minute. We'll finish it off quickly, right? V1 to V2 to V3. Sorry, V1 to V2 to V3. That is 1 over C1 to 1 over C2 to 1 over C3. What is 1 over C1? 1 over 1 to 1 over 4 to 1 over 2. And you need to multiply everything by LCM. And I think LCM here is 4. You just multiply by 4. It is 4 is to 1 is to 2. 4 is to 1 is to 2. So V2, it's going to be equal to, how many portions are there here altogether? We have altogether 7 portions, right? So out of 7, 1 for V2. Out of 7, 1 for V2. 1 over 7 multiplied by the total voltage, that is 2.8. 2.8 over 7, 0.4 volt. That is the answer for V2. And then we go to the other other two capacitors actually. V4 over V5. Now V4 over V5 is not that hard. It's pretty straightforward. V4 over V5 can be written as C5 over C4. C5 over C4. So what is C5? 5 divided by 3. 5 divided by 3. If not, yeah. Okay, 5 divided by 3. So we are supposed to find V5. V5 is 5 and 3 means 8. Total 8. Out of 8, 3 for V5. 3 into total voltage is 2.8. Okay. Now if you simplify this, you will be getting, we'll simplify 2.1 divided by 2, isn't it? 2. How did it become 2.1 divided by 2? I simplified up and down by 4. So this is 0.7. This becomes 2. 3 into 0.7 is 2.1. Here 2. And final answer is 1.05 volts. So 0.4 and 1.05 should be the answer. Now let's imagine they have given you a circuit like this. Okay, right. So you must be wondering what's so different from the questions we did before. Now, let's say they have given you points. Now, this point is, I'll mark those points in different color. This point is A, this point is B, this point is C, and this point is D. Okay, right. And B is grounded. B is grounded. B is grounded. This is how they will give you, this is the symbol or sign rather they will use to say that B is grounded. Okay, point B is grounded. And they are asking you to find, let's say they are asking you to find, this is the question. What is the electric potential at point B? That is the question. So what are we going to do if you come across a situation like this? Now we normally you will understand more if you have done electricity, but since we haven't studied electricity yet, as of yet, let's focus on this. Fine. Now the procedure with the voltages is same. Okay, same old. So I will take 1 minute and quickly find these things: V1, V2, and V3. Right, V1, V2, and V3. Let's find them out very quickly without writing too much. Now V1 to V1 to V2 to V3. That is going to be 1 over 3 to 1 over 2 to 1 over 4. Right, 3 to 4. What is the LCM? 12. Multiply them by 12. 4, 6, 3. Okay, so total we have 13 portions. Therefore V1 is going to be equal to 4 out of 13. 4 over 13 multiplied by 6.5. 4 over 13 multiplied by 6.5 is 2 volt. V2 is 6 out of 13 multiplied by 6.5. 13 and 6.5, if you simplify, it's 0.5. 0.5 into 6 is 3 volt. Then what is V3, people? V3 is here 5, here 6.5, 1.5. I have calculated them very quickly because we have done it quite a few times now. Right. If this is 0, No, I'm sorry. If B is grounded, you should know the electric potential there is zero. I'm talking about electric potential. Electric potential and voltage are not same. Voltage is electric potential difference. Okay. Right. Now, what is electric potential then? At this point, it's zero. Now, what is the value of V1? V1, the value of V1 is how much? 2 volt. Okay. Value of V1 is 2 volt. Right. Value of V2 is 3 volts. Value of V2 is 3 volts. And value of V3 is 1.5 volts. All right. So if this point is 0 and this side is the positive side of the battery, we all know high electric potential, low electric potential, then this side should have the higher electric potential. If this is 0, this side should have the highest potential because that side is connected to plus. And this 2 is called electric potential difference. So if this is 0, this has to be 2. This has to be 2 volt to get that difference. Now, 2 minus 0 is 2 volt. 2 minus 0 is 2 volt. That is what electric potential difference means. And then what is the potential at C? What is the potential at C? The potential at C should be minus 3 volt. Minus 3 volt. Why is that? I said the side which is connected to positive of the battery should have high potential. The side connected to negative side of the battery should have low potential. So the difference between voltage at B and voltage at C should be 3. This is already 0. So this has to be minus 3. This has to be minus 3 because here high voltage, low voltage, that means to the right, it should be even more lower, even lower, even lower. Okay, 2, 0, minus 3 volt. Now, what about point D then? What about point D? Okay, for a change, let's take this as VD for the time being. VD. I'll take it as VD. So, my point is minus 3 is okay. If not, VC minus VD is equal to this 1.5. That is how the equation works. The potential to the side where the positive of the battery is connected minus potential to the side where the negative of the battery is connected. That will give you the potential difference. So what is VC potential at C? That is minus 3. What is VD? We have to find equal to 1.5. So minus 3 minus 1.5 is only equal to VD. Therefore, VD is equal to how much? 4.5 volts. 4.5 volts. That is how it works. Hope you all understood that. 4.5 volts. Okay. So when you see this sign, you have to be extra careful. It means at that point, voltage is 0. It's grounded. At that point, voltage is 0. Okay. And based on that, you have to go ahead. Now, this is an example from 2002 past paper, 48th MCQ. Right, now let's see what that question is all about. If point P is maintained at a constant potential of 1100 volt, the potential difference across AB, is given by, right, fine. Now, first thing you have to understand is P is at 1100 volt and D, you can see it's grounded. Therefore, potential at D is going to be 0 volt, 0 volt, electric potential. Therefore, the overall potential difference between point P and point D, that is how much? 1100 volt. 1100 volt. That is the overall potential difference. 1100 volt. All right, and 1100 volt. So they are asking us to find the potential difference across this one, V1. So I'll take, just like usual, we will take it as V1, V2, V2 rectify. V1, V2, and V3. I think we need a similar question. It should not be very hard. V1 to V2 to V3, that is equal to 1 over 1 to 1 over 2 to 1 over 3, and that is, you have to multiply everything by 6 to get rid of this. So 6 is to 3 is to 2, and total portions, how many? You have 11, and we need to find V1, potential difference across AB. So V1 is going to be equal to, out of 11, 6 multiplied by total voltage, that is 1100. That will be 600 volt. So as complicated as the question we did just before, so just want to show you where sometimes they will give you with grounded. Okay. Now, yeah, they will give you circuits like, sorry, systems like this where there is no battery or loop is given. So you have to just carefully handle it. Now the approach to this question, this is a question from 1995, a 19th question. It's completely completely different. Because in the previous circuits we discussed, the circuit looked like this. I mean, if I draw this circuit according to the previous diagrams we drew, that circuit should look like this is the kind of circuit we were drawing. There were 3 in series, but now there is something different about this circuit. There is a resistor put in the middle. They have put a resistor in the middle. Okay, so whenever you do capacitor questions, you should understand one thing, that is current has flown through the system and the capacitors are now fully charged. There is no current in the system now. Now, if there is an alternative path for the current to flow, it will flow. But what happens here is, you can see current has to start from the battery, and let's say it avoids this part because there's a capacitor. Okay, even if it goes this way, it has to go through the capacitors. So can't help. Okay, so if current starts from the battery, current has to reach the end of the other end of the battery. It can't reach the other end of the battery without going through the capacitors. Therefore, at steady state, that means once all the capacitors are charged, there is no current in the circuit. I is equal to 0. There's not going to be any current in the circuit. Because if current starts from the battery's positive terminal, it should end up at the negative terminal. It can't do that because there are fully charged capacitors here. Okay, right. Now, there is no current flowing through this 8 ohm resistor, so there won't be any potential drop across this. Because we know for resistors, what is the equation for voltage? Voltage is equal to IR. If current is equal to 0, voltage is equal to 0 across a resistor. Therefore, there won't be any voltage across this potential difference, right? So since there is a wire like this, people, you have to understand one thing very carefully. The potential at this point, electric potential at this point, if I take it as V, will be same as electric potential at this point, because it's a wire. It's a wire connecting this and this. There is a resistor, but across that resistor, there is no potential difference because there is no current. If there is no current through the resistor, according to this, there is no potential difference. If there is no potential difference, this is also V, this is also V. Now, if this is V, this is also V because there is no resistor or capacitor. Therefore, whatever the electric potential we have here, we will have here as well. And this one also will be V. If there is no resistor or capacitor, then same voltage, not voltage, sorry, electric potential will be there. Now, at this point also electric potential is V. At this point also electric potential is V. Therefore, the potential difference across this capacitor, it is equal to 0. V minus V. It will be 0. We call it short circuiting. So this capacitor is short circuited. This capacitor is short circuited. Same thing will happen. Imagine you have a system like this. If you put a piece of wire like this, what are you doing? You are making this potential and this potential equal. If you put a wire like this, therefore the potential difference across this becomes 0 if there is no potential difference across a capacitor. Now go back to capacitor. This is for resistors, no? For capacitors, what is the equation? For capacitors, the equation we use is Q equal CV. If V is equal to 0 for a capacitor, Q is equal to 0. If Q is equal to 0 in a capacitor, the capacitor is not charged. That means that capacitor is useless. All right. So in this question, you have to consider only these two capacitors. If you consider 3 micro ohm, then your answer is wrong. So some of you have got 11 volt as the answer. What you have done is you have taken 1 and 2 and 3, all 3. That is unfortunately incorrect because Across this 3 microfarad capacitor, the potential difference will be 0 because there is a wire connected like this, and it is short circuit. Okay, so what is the question? A battery is connected to 3 capacitors and a resistor as shown in the circuit diagram. If the voltage across the 2 microfarad capacitor is 3 volt, the EMF of the battery. The EMF of the battery means the voltage of the battery. Now, for our convenience, I will redraw this circuit. So there is a battery and there are 2 capacitors. 1, 2. That's all. I have drawn only the capacitors which will be charged. This capacitor will not be charged. So here we have 1 microfarad and here we have 2 microfarad. All right, C1 and C2. Right. C1 and C2. And across this, it is V1. Across this, it is V2. And the total voltage is what we are supposed to find out. And in the question, they have given us V2. V2 is it? Yeah, 3 volt. V2 is equal to 3 volt. Now, what is the approach? V1 over V2. If not, V1 to V2 is equal to, V1 over V2, let's take that thing, equal to C2 over C1. And what is C2? 2. C1 is 1. Okay. So, you can see V1 to V2 is actually 2:1. And if you want to find V2, what is the equation you are going to write? V2 is equal to, out of 3 portions, 1 into total voltage. That is going to be the equation. So for V2, we have to substitute 3 here, equal to 1 over 3 into V, and that will give you V is equal to 9 volt. V is equal to 9 volt. 9 volt is the, V is the voltage of this battery. EMF of the battery. EMF means electromotive force, the voltage marked on a battery. So the correct answer for this question is 9 volt. 9 volts. Okay. Now you will get the same result even if you have put just a wire without the resistor. Even if you have put just a wire without the resistor. I mean, if you have a system like this, still you are going to get the same answer because when you put a wire, what do? You are short circuiting this. Now you must be asking, okay, there's a resistor here now. Then what won't that resistor do anything? No, the resistor will not do anything because there is no current going through the resistor. If there is no current through a resistor, people, then there is no use with that resistor. It's like that resistor is not there if there is no current going through that. Okay, so for a system like this and for a system like this, it's going to be the same result. So next point we are going to discuss is dead capacitor. What is a dead capacitor? Now, if you have a circuit system, in that there will be a battery, there will be a lot of capacitors, sometimes resistors and everything. And there are certain capacitors, we can ignore them. Such capacitors are called dead capacitors. Dead capacitor says the capacitor will be there, but in that capacitor charge will not be stored. If not, the potential difference across that capacitor will be 0. Okay, so I'll say dead capacitor, we'll write about it. A capacitor in which no charge is stored. No charge is stored. Or a capacitor across which electric potential difference, if not one word for that, is voltage. Electric potential difference or voltage is 0. That is what you call a dead capacitor. Okay, right. Now under that, let's discuss some examples. First example we have already discussed, that is a short circuited capacitor. A short circuited capacitor. Now how do you identify a short circuited capacitor? A few examples. I'll quickly draw a few examples. Imagine a situation like this. There is a battery. Then there are a few capacitors. There's another capacitor. Okay, I'll draw 3 of them. And imagine they have done something like this. They have put a wire like this. Just a wire. Okay, just a wire, conducting wire. That's all. Nothing else. So when you put a conducting wire like that,
I think we discussed this before. At this point and this point, the potential becomes same electric potential, same electric potential. Therefore, the potential difference across this, I say delta V, potential difference across this is 0. Therefore, this is a dead capacitor. So I'll highlight that in yellow color. This is a dead capacitor. This is one of the examples for a dead capacitor. Sometimes they will do this. Oh, it does not really have to look like that. Another example is the previous question we discussed. If you have a system like this, there are one capacitor, then another capacitor, and then there's another capacitor, but you have put a wire like this, just a wire like that. Or even if there's a resistor here, since there is no current going through that resistor, it's like the resistor doesn't exist. So it's like a normal wire. So when there's a normal wire, once again, what's the problem? At this point and this point, or else at this point and this point, the potential is same, because you have connected just a conducting wire. So potential will be same. Therefore, again, potential difference across this is 0. This is another dead capacitor. This is another dead capacitor. Another dead capacitor. Okay, fine. So these are some examples for dead capacitors. In addition to that, what can I say? It doesn't really look. You should be able to figure it out from the diagrams. That is very important. You should be able to figure it out from the diagrams, people. Yeah, you should be able to figure it out from the diagrams. That's pretty important. Huh? Now, what happens when there's a dead capacitor? Now, this is a past paper question. Well, let me show you that. Right. So this is that question I was talking about, where short circuiting capacitors is going to be used. Fine. Let's move on. This is from 1998, 22nd question. All right. 4 identical capacitors are connected as shown in the figure. The equivalent capacitance across PQ is 0.1 microfarad. Equivalent capacitance across PQ. So 4 identical capacitors means C. Okay, they have given C. Okay, they have given. Right. If the points R and S are connected by a wire, equivalent capacitance across PQ will become, okay, right. So initially they have given us the equivalent capacitance, and now they're asking what will happen if I put a wire here. Now, before putting a wire, let's find out the equivalent capacitance. Before putting a wire, let's find out the equivalent capacitance. Wait a minute. Right. Now, between P and Q, it is one line like this. It is one line like this. Therefore, it is a series connection. Okay, it's a series connection. Before wire is connected to R and S, what can I say? Equivalent capacitance. I'll put equivalent capacitance is equal to, there are 4 capacitors in series. If there are 4 capacitors in series, the equivalent capacitance is C over 4. Okay, and the equivalent capacitance given to us, that is how much? 0.1 is it? Yeah, 0.1 equal to C over 4. Therefore, C is equal to 0.4 microfarad. 0.4 microfarad. That is the value of each of these capacitors. 0.4 microfarad. Here also 0.4 microfarad. Here also 0.4 microfarad. Okay. Now, when wire is connected to R and S, when wire is connected to R and S, let's see what's going to happen. When wire is connected to R and S, this is what's going to happen. Let's draw the diagram again very quickly once again. Yep, 1, 2, this, and then here another one. Yeah, okay. This is where the wire is put, right? They are connecting the wire like this. If you put a wire like that, what's going to be problem now? This is point R, point S. Yeah, true. Voltage at this point, sorry, not voltage, potential at this point and potential at this point will be equal. Because when there is a wire, that is how it is. I mean, there is no way the potential is going to be dropped. For there to be a potential difference, you should have a component here, a bulb, a battery, a resistor, a capacitor, something like that. It's not there now. So at this point and this point, potential is same. Therefore, across these 2 capacitors, electric potential will be 0. I mean, electric potential difference, voltage will be 0. Voltage will be 0. Because they are what? These two capacitors are short circuited. They are short circuited. And remember, P and Q are here. So we are supposed to find out the equivalent potential resistance, sorry, capacitance across P and Q, right? So this time C equivalent will be given by C by 2, because we are going to disregard this capacitor and this capacitor because they are short circuited. You put a wire, then these will not work because current will only flow through this, right? This will not work. Therefore, C, I think we found C already. It's 0.4. So 0.4 divided by 0.4 divided by 2. Final answer is 0.2 microfarad. 0.2 microfarad. Therefore, the answer is third. That is how we have to approach short-circuited capacitors. And then the second type, it's called a Wheatstone bridge. Wait, I will explain that. Second type, it's called Wheatstone. This is the name we give, okay? Wheatstone or Wheatstone bridge. You will be coming across this in electricity also. One of the most important parts, right? One of the most important parts. So talking about what is a Wheatstone bridge. Now, what is a Wheatstone? You should be able to identify the Wheatstone bridge carefully. I will wait. First of all, let me give you the layout of that. Let me give you the layout of that. Now, it will look like this. It will be a system of capacitors like this, people. One, there will be one, two, and then there will be a capacitor in the middle, like this. And then there will be another capacitor like this. This is okay. Then it will go like this, and then so this you can see it's a capacitor scheme like this. This might have been given to you like this also. So you should be able to identify the similarity between them. It's just the shape is different, but it's actually an identical circuit. These two. Now, this if you take this point as A and this point as B, if you take this as A and this as B, it's the same thing. It's the same thing. So this is C1, C2, C3. No, we'll take the C5 here in the middle. C3, C4, and here C1, C2, C3, C4, and the middle one is C5. Sometimes, let's say there are two capacitors here. That means you have to take the resultant of those two capacitors and make them one. Okay, likewise, you have to make them one. Now, we are talking about dead capacitors, types of dead capacitors. So here the dead capacitor is going to be this capacitor if a particular condition is fulfilled. Okay, now we are looking for a dead capacitor. This is the dead capacitor, the one in the middle. But it will not always be dead. It will be dead if a certain condition is satisfied, right? So C5 is the capacitor of focus. C5. Let me highlight that properly. C5, right? In both, it's the same diagram. Just in one is rhombic in shape, the other one is rectangle in shape, right? C5 will function as a dead capacitor if conditions are, if the condition is this one over this one, C1 over C2 is equal to C3 over C4. Okay, the ratio between these two should be equal to the ratio between these two, or you can say the other way around. C1 over C3, the adjacent ones, C1 over C3 should be equal to C2 over C4. I mean, the first equation, if you cross multiply it, you will get the same thing. Oh, wait, no. Oh, yeah. Okay. Cross. You put this down, you put this up. Same thing. Not C1, C4, C2, C3. Not diagonally. No. It's the adjacent ones. Okay. This is the most important condition. Now, let me give you some examples. Now, if you have a system like this, very quick example so that you can handle questions carefully. If you have a system like this, right. If you have a system like this, give me a sec, right? system like this. Here A, here B. Normally they will give all four equal, all five equal. C, 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 C. Right, now look at the ratio. 1:1, 1:1, 1:1, 1:1. So okay, the ratios are equal. This is 1:1. This is also 1:1. Then this is going to be a dead capacitor, the one in the middle. There will be no charge. This is a dead capacitor. It is a dead capacitor. Why? Wait. It's a dead capacitor. So charge equal to 0. Now let me explain you why is it a dead capacitor. Why is it a dead capacitor? That's the question we all have, correct? Fine. Now I think it would be better if I explain this to you with numbers. I think it will be easier for you to understand with numbers rather than symbols. Okay. So let me do that with numbers very quickly. Example, or else I just say explanation. Explanation. Right. First of all, let me choose capacitors with relevant values. The middle capacitor, it can have any value. Okay, but the capacitance of that can be anything. Right, now this is let's say 2 microfarad. All right, 2 microfarad. This one is what, a 6 microfarad, and then this is 1 microfarad, and this is 3 microfarad, and let's say this is 7 microfarad. I'll just put right, fine. And according to the theory, now you can see this is now let's take capacitors C1, this is C2, this is C3, and this is C4. Look at the ratios. C1 over C2 is equal to C3 over C4, and that is how much? 1 over 3, isn't it? 1 over 3. It satisfies this what do you call that condition? So based on that, we can say 7 microfarad is a dead. 7 microfarad is a no. I will name it. We'll name it. I'll put C5 here. Right. So C5 is a dead capacitor. Now the question is why? Why is it dead? How is it dead? Is a dead capacitor. Right. Now why is it dead? Right. Fine. For a while, just forget about this 7 microfarad. Let's forget about this 7 microfarad for a while. Let's put the capacitors, the other 4 capacitors, and see. We're going to check something. Right. I'm going to disregard that 7 microfarad for a while, and I'm going to check this. Now this is 2 microfarad, people. 2 microfarad, and this is 6 microfarad, and this is 1 microfarad, and this is 3 microfarad. Okay. Imagine they have given us a voltage, I mean potential difference. The potential difference across the system is let's say 3 volt. Okay, 3 volt means at this point it will be 3 volt, and at this point it will be like 0. We'll take like that. Right. So if at this point if it is 3 volt, at this point and this point it is 3 volt, 3 volt. Right. At this point it is 0 volt, and here also 0 volt. Right. Fine. So 3 volt is going to be shared between 2 microfarad and 1 microfarad without any calculations. Can you tell me what is the potential difference here? What is the potential difference here? Hurry up. What will be the voltage here across each what capacitor? Across this and across this. Can you tell me quickly? Because we have done it, right, many times. What are the voltages? This is going to be 1 volt. This is going to be 2 volt. Because voltage we have learned now, V1 over V2 is equal to C2 over C1. V1 over V2 is equal to C2 over C1. So 3 is going to be separated like this: 1 volt, 2 volt. So what is the potential at this point? What is the potential at this point? 3 minus 1. So the potential at this point is going to be 2 volt. Potential at that point is going to be 2 volt. Right? Similarly, what is the potential difference across this and potential difference across this? Tell me quickly. What is the potential difference across this and this? Hurry up. 3 volt is the total voltage. 6 and 3. 2 is to 1. 6 and 3, 2 is to 1. Again, it will be 1 volt and 2 volt. It will be 1 volt and 2 volt. So 3 volt here 1 volt here. Therefore, what will be the potential here? 2 volt. Now, don't ask me how did this 3 come. It was just a random value. It could have been 4, 5, 6, anything. For any value, if you do the calculation, you will get the potentials at each point, at these 2 points, equal. Okay, right. Now, if I put something here, anything, if I put something here, what will be the potential difference, people? What will be the potential difference? What will be the potential difference? 0. Same potential, same potential. At these 2 points, potential will be same because that is how the capacitors are distributed. Capacitance of capacitors are distributed. Okay, so this is the explanation for that. You don't have to explain this every time you want to use it. As long as you can figure this out from a circuit system they have given, then you can consider this one to be a dead capacitor. This one to be a dead capacitor. Then your circuit gets much simplified. Then you can continue. Right. So fine. So let's keep this in mind hereafter. A very important aspect. Ratio. How is the ratio? C1, the adjacent capacitors. C1 divided by C2 should be equal to C3 divided by C4. All right, fine. Right. So let's say they have given you a capacitor system like this. Is C a dead capacitor? That is the question. Is C a dead capacitor? Is it a dead capacitor? Now here there aren't only 5. There are 1, 2, 3, 4, 5, 6, 7 altogether, right? But you should be able to see it as 5 capacitors. Should be able to see it as 5 capacitors. Why? These two are in series, right? 6 and 3 are in series. Therefore, you can find the equivalent capacitance of those two. So what is the equivalent capacitance of those two? 6 and 3. It will be 2 microfarad if you find it. How do you find the equivalent capacitance of parallel capacitors? You multiply them and then you divide it by the addition of them. 6 into 3 is 18 divided by 9. Addition is 9. So here 5 microfarad. So like 2 microfarad, 5 microfarad, and here we have 4. And what will we have at the bottom, people? What will we have at the bottom? 220 microfarad capacitors are connected in series. So 20 divided by 2, that will be 10 microfarad. Okay, look at the ratio. 2 is to 5 is equal to 4 is to 10, correct? 2 is to 5 is equal to 4 over 10. So C is a dead capacitor. C is a dead capacitor. All right. Fine. Good. Right. One more time. Right. So this is where you guys are going to be a bit confused, I think. Let's see. Fine. No. Oh, I made a mistake here. Okay. Right. Current has to go somewhere. Okay, fine. Let's say this is 2 microfarad. This is 8 microfarad. This is 3 microfarad. And this is 12 microfarad. And this is C. Okay, now tell me, C a dead microfarad, sorry, dead capacitor or not? This one. Is C a dead capacitor or not? Is it a dead capacitor or not? C. This is not a dead capacitor. It is not a Wheatstone bridge. It is not a Wheatstone bridge. not a Wheatstone bridge. For it to be a dead capacitor, first thing, it has to be a Wheatstone bridge. Now, okay, 1:4, 1:4. But look at this part. Look at this part. In a Wheatstone bridge, this and this are not in series. Here, this part is separated by this. This part is separated by this. But here, where is this line? The line is missing here, correct? So these 3 and 12 are actually, they are in series. They are in series. So this system can be altered to this. C will be there, 8 will be there down. These two are in series. Therefore, you can, instead of those two, you can put one single capacitor like this. So this is a 2 microfarad. This is 8 microfarad. This is C, and 3 and 12 in series. It will be, I think, 2.4. 4 more 12s required. 12 by 5. 12 by 5 is 2.4. This is 2.4 microfarad. This one. I hope you understood it. You don't have this structure. You don't have this frame, this there. You should have this structure. One should be here, one should be here, one should be here, one should be here, one should be here. Here we don't have that. This is a series path. Therefore, here C is not dead. Careful. When you do questions, you have to be a little careful. Okay, the frame. Look at the frame. Look at the Wheatstone bridge. It should be like this, or it should look like this. These two lines must be, these two must be there. Then only you can talk about Wheatstone bridge. But here we don't have that line. These two are in series. So it is not a Wheatstone bridge. Therefore, you can't consider a dead capacitor here.